Ampere's law. Using the Biot-Savart law, we were able to show that for a long straight wire carrying a current I, the magnetic field in the vicinity of that wire was given by B equals mu naught I over 2 pi r, and the direction of B is tangent to a circle about the wire. So let's take a little cross section. Of course, the wire extends forever. So above this wire, our magnetic field would point to the left. Below the wire, it would point to the right. And at any point about the wire, the magnetic field is tangent to a circle about the wire. Suppose we multiply both sides of this equation by 2 pi r. We find B times 2 pi r is equal to mu naught times I. 2 pi r is the circumference. That's in fact the circumference of this circle right here. That reminds us of something, that this left side of the equation would in fact be the integral of B dot ds around that circle. It's a complete path, so that would in fact be a closed integral over a closed path. If we were to do that integral, B dot ds, B and ds are parallel everywhere on that circle, and so that would just be equal to the integral of B times ds. Because they're parallel, the dot product would just give us 1. B by symmetry is the same magnitude, and of course by our equation up there is the same magnitude everywhere on that circle. So that would be B times the integral of ds, and yes, this is a closed path. And so the integral of ds is just the length of the path, which is 2 pi r. B times 2 pi r, which is what we had up here from our Biot-Savart law expression. Now, it turns out that this expression right here is true in general, that we have the integral of B dot ds is equal to mu naught times the current. This relationship right here is called Ampere's law, after the fellow who figured it out the first time. And the current here, well, what current? Well, for a wire it's obvious. More generally, for any arbitrary problem, the current is the current that pierces the surface bounded by the path over which we do the closed integral. So if taking an end view of the wire, we've got the current coming toward us. If we had our path going around like this, well, what is the surface that we're referring to, having the current penetrate, the current pierce? Well, that is just the surface that is bounded by the path that we're integrating over. So we could imagine stretching a fishnet here, connected to whose edges are that path, that Ampere's law path, that dashed path there. And so what current penetrates through that fishnet is just the current in the wire. This will be true in general. And so we might add a little sub p over here to remind us that this is the current piercing that surface bounded by the path. This ought to remind you a bit of Gauss's law, where with Gauss's law, we were concerned about the flux through a surface. We had a closed surface. Here we have a closed line, and it's the current through the surface bounded by the line that's important. Remember, for Gauss's law, we said that Gauss's law is always true, but it's not always useful. It was useful in solving problems of high symmetry, highly symmetric charge distributions. Similarly, Ampere's law will be useful in solving problems for very symmetric current distributions. Of course, an infinitely long straight wire is a very symmetric current distribution. So let's look at some examples of the kind of problems we might be able to solve using Ampere's law. Now let's look at the current inside that long straight wire. So I'll blow it up a bit, make it a little easier for us to follow. So there's our wire. There's a cross-section of a wire. It's going off to infinity, and of course it goes off to infinity in the direction toward us as well. It's carrying a current I. So what is the magnetic field a distance r from the center of that wire? And let's assume that the radius of the wire is a. All right, so a is the radius of the entire wire. Well, to do this, let me draw it another way. We'll have an end-on view. Just make it a little simpler. We're interested in the magnetic field right here, and the current, let's have the current coming out of the screen going toward us. In that case, the magnetic field will be, the magnetic field lines will run counterclockwise. So we need to construct our Ampere's law path at the spot where we're trying to evaluate the magnetic field. And so right here will be our Ampere's law path. That's the path we're following right there. We'll walk around to do our integral. So we have for that path, using Ampere's law, the integral of B dot ds is equal to mu naught times the current piercing the surface bounded by that path, I piercing. Now what surface are we talking about? This surface right here. This is the surface whose edge falls along our Ampere's law path. This is the fishnet we're talking about. This little circle of radius r. So how much current is flowing through that? Well, the current density is just the current per unit area. We'll assume uniform current density throughout the wire. That's a reasonable assumption. And so the area is just of the wire is pi a squared. A is the radius. And so the current that's piercing that blue surface there, the surface bounded by my green Ampere's law path, is just equal to the current density times the area of that radius r circle. And so that J is I over pi a squared. The radius of that blue surface is pi r squared, and so that then just gives me I times r squared over a squared. I guess that should have been obvious to us. The fraction of the current going through the inner circle is just the same fraction as the fraction of the area that the inner circle represents of the total wire cross section. So we can plug this back in our expression up there. Mu naught times I r squared over a squared. Now on the left side, well, we've done that integral before. We know that's just going to be equal to b times 2 pi r. Dividing both sides of the equation by 2 pi r, we get mu naught I divided by 2 pi a squared, and the numerator will have an r left. The r from the left side will cancel our r squared. So there we have our magnetic field inside the wire. Notice that the magnetic field is 0 at the center where r equals 0, then increases linearly as we move out to the edge of the wire, reaching a maximum value at the wire surface. Outside, we would use that same expression we had derived earlier. We would find that B then falls off mu naught I over 2 pi r. But inside, it is increasing linearly. See how easy this is. There's not a lot of math there. The integral on the left side will always go something like this. It'll be a pretty easy integral. If we pick the right symmetry, the integral ought to be easy. It's only those kinds of problems where Ampere's law is useful, those high symmetry problems. The right side is a matter of figuring out how much current is piercing that surface, that blue surface that fills in the space bounded by the Ampere's law path shown here in green. Let's tackle one more problem. Let's consider the case of the very common case, a very practical case of an electromagnet. We call it a solenoid. It's a long coil. It's a very practical problem because this is the way we make electromagnets. So we're going to wind a tight coil, lots of turns here, round and around and around. We'll try to keep the radius as constant as we can, and then we'll peel it away. I didn't finish up so well on that, but you get the idea. So here we have a long coil. Now, to be able to solve this problem, it will be easier to envision this if we take a cross section. So imagine that we're taking the side view, and we're going to slice this with a surface right through all of those wires. So we have a wire coming in, it goes in through the screen, executes a little semicircle behind the screen, the wire pops out of the screen right here. We have a semicircle coming out toward us, going back into the screen on the top side, makes a semicircle on the back side, pops out again, going through the screen, and so on. So we have these are our cross sections of the wires that we're slicing as we work our way down that long coil here. So this is just a similar view, but just taking it in cross section rather than seeing that whole 3D coil, which is rather hard for me to envision anyway. Just looking at that picture up there, this is easier. Alright, so there is our coil. The current's going in through all those wires, and the top half, they're popping out of the screen, and the bottom half. And this helical path for the current is what makes our solenoid. And we'll have the current going here, of course. All right. What's the direction of our magnetic field? Let's think about that for a moment. Well, if you could go back to the Biot-Savart law and find the magnetic field direction at the center of each loop. And in fact, the magnetic field should be going from right to left through here. The magnetic field ought to be going right to left. Now, will it be exactly straight? Well, it depends on how tight the coils are. If we get close to it, the wires, individual wires, we'll probably see a little wiggle like that. But if they're thin wires, tightly packed, until we get very close to them, it ought to be pretty straight. What about the direction of the magnetic field outside? Well, it's going to be like the magnetic field due to a bar magnet, in fact. All right. So this is our magnetic field. Where's a good place to pick our Ampere's law path? This takes a little bit of cleverness here until you've done one or two. One thing we always want to do is to pick our path where we're trying to find the magnetic field. And in this case, we want the magnetic field inside, so we will pick at least one leg of our magnetic field right inside the coil. All right? So that's one leg. We're going to need to enclose our wires, and so that means pulling our path out this way so that the wires will be going through the surface whose edge is our path. Now here's where the little bit of cleverness helps out. The magnetic field outside we don't understand so well. Let's go way out here, a long way. In fact, imagine it going down, to 50 miles down that way, so that on this last leg the magnetic field is 0. We won't have to worry about that. Let's call this leg 1, leg 2, 3, and 4. On 2 and 4, the magnetic field is pretty much perpendicular to our ds. When we walk, let's walk around this counterclockwise, and so we would have a ds pointing that way over there, and a ds pointing up over here. Those are more or less perpendicular to the magnetic field, so we're not going to get much contribution to our line integral. So let's start writing down what we have. So our closed integral of b dot ds is in fact going to be 4 integrals. The integral of b dot ds over leg 1 plus the integral of b dot ds over leg 2 plus the same for 3 and 4. Ditto, ditto. Well, all of these are 0 for the reasons we just explained, and we're just left with the integral of b dot ds inside. Well, if we're not close to the ends, and we'll make that approximation, if we're not close to the ends, we expect the magnetic field to be pretty uniform, because as far as you can see one way or the other, you just see coils, coils, coils. So, and also notice that b and ds are parallel. So we have the integral of b dot ds is equal to b times ds, integral of b times ds. B is pretty constant. We'll bring it out. Now, admittedly, we're making some approximations here. B times the integral of ds. What is that? It is just, the integral of ds is just the length of leg 1. So we will have BL. So my integral of b dot ds is BL. Well, remember, what does Ampere law tell us? Ampere's law tells us that the integral b dot ds is equal to mu naught times the current piercing the surface bounded by the path. Well, what is that current? Well, first of all, what is the surface? The surface that is bounded by our path, our little fishnet surface, is just this right here. It's this rectangular surface bounded by our green Ampere's law path. All right, so how much current do I have? How much current do I have piercing that surface? Well, every wire that goes through contributes an I, let me just call this current up here I naught, the current in the wire. Well, each one of these wires that goes through, 1, 2, 3, 4, 5 of them, contributes to current I naught. And so in this case, it would literally be 5 I naught. But more generally, let's just call that mu naught times the number of turns of the wire times the current in that wire. It'll be equal to B times L. So let's just solve for B, and we get B is equal to mu naught N over L times the current in the wire. Or we could just write that as mu naught times little n I naught, where we define little n to be just the number of turns per unit length. Well, this is a really interesting relationship. It tells us the magnetic field. First of all, notice we did not use in this problem exactly where within the solenoid we were. It could be at the center or further out toward the edge. As long as we don't get so close to the edge that the the structure of the wires are highly visible. That is, if we'll stay several wire diameters away from the edge, this should be a pretty accurate approximation. And so everywhere within that linear coil, we get a magnetic field that's pretty constant. It has a value of proportional current. That makes sense. It's an electromagnet. Double our current will double our magnetic field. But the other thing that's fascinating is we want a very powerful magnet for a given current. What we need to do is pack a lot of turns in per unit length, a lot of turns per meter, per inch, per centimeter. That's our little n there. Very fascinating result, really straightforward calculation, taking advantage of this new law that we've discovered, Ampere's law, that tells us a convenient way of calculating magnetic fields for reasonably symmetric current distributions. Thank you.